This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the October-November 2021 Mechanics M1 paper. This is paper 4 variant 2 from the 9709 syllabus. And this question here is about statics, and we have a block of mass 5 kilograms being held in equilibrium near a vertical wall by 2 light strings and a horizontal force of magnitude x newtons as shown in the diagram. The 2 strings are both inclined at 60 degrees to the vertical. Given that x is equal to 100, find the tension in the lower string. Okay, so I've just drawn the diagram down here so that we can have a look at this and not have to keep scrolling up and down. So now we've got this object which has a weight which acts vertically down. Okay, so the weight of this object is 5g newtons. And we have the tensions in the string which will be acting in relation to the object towards the wall. And they're 2 separate strings, so that the tensions will be different tensions. I'll just draw them like this. Just do this. Okay, so you have the tensions in the string. So this is the tension in the upper string. I'll call it TU. And this is the tension in the lower string. I'll call it TL. Because they've said it's lower now. So I'll put it like that. Okay, so they're not the same tension. Okay, in fact, what I'll do is just to make it a bit better, I'll call it T1 and T2. Okay, so T1 and T2. So you have the tension in this string, which is T1, and this tension in the lower string, which we'll call T2. All right, so now, what we have here, just gonna make some space. So we know that X is 100. So this is 100 newtons here, pulling in this direction horizontally away from the wall. So we got to find the tension in the lower string. Okay, so what we can do here is we can think about resolving the forces acting on this particle horizontally and vertically. So the X and the weight are both, the 100 newtons and the weight are both already horizontal and vertical. So we have to resolve the forces T1 and T2 horizontally as well as vertically. So we have to think about what angle this is over here. So here we have, well, this whole angle here is going to be 60 because this is an isosceles triangle. 60, 60, 60. Right, if this is 60, this is 60, that must be 60 because this triangle, the sum of the angles is 180. And this is going to be the bisector of the angle. So this is going to be 30 degrees. And this is also going to be in this side 30 degrees. Right, so if I want to resolve this tension, or these 2 tensions in the direction which is going away, or in the direction which is vertical, T1 will have a component up like this, and T2, and also a component like this, and T2 will have a component which is vertical but down, and also horizontal like that. So they'll both have components like this. So as we know, if I want to resolve the force going into the angle, like I'm resolving this force in this direction, horizontally, I have to go into the angle given. The angle given is 30 degrees. I have to go into the angle. As I'm going into the angle, it's like I'm finding the adjacent side. It's like the adjacent side. So I have to use cosine. So this is going to be T1 times cosine of 30. And if I'm resolving in the direction going away from the angle given. So this is the force I want to resolve vertically. So I have to go away from the angle given. This is like I'm finding the opposite side. So I'm going to be using the sine. So I'll be using T1 times sine of 30. T1 times sine of 30. Okay, and on this side, very similar kind of situation. Okay, this one here, we're going to be resolving this in the direction going into the angle. It's going into the angle, as we can see. So this is going to be T1. This is going to be, sorry, T2. T2 times cosine 30, and this will be, let me just draw it properly vertically, it's a bit of an angle. This one, you're going away from the angle, so it's going to be T2 times sine of 30. So this is T2 sine 30. So now if I consider the forces acting and resolving the forces horizontally, okay, we know this is an equilibrium, so the forces acting to the right and the left are equal. So I can say 100 is equal to T1 cosine 30 plus T2 cosine 30. And if I resolve the forces acting vertically, I can say that the forces acting upwards, T1 sine 30, is equal to the force acting downwards, which is 5 times G, plus T2 sine of 30. So I'm going to take these two equations and I'm going to just simplify them a bit. I know that cosine 30 is root 3 over 2. The cosine of 30 is the same as root 3 over 2. I'll keep things in exact form for now. And I know that the sine of 30 is equal to a half. If you don't remember that, you can use your calculator to find that. But we should know those exact values by now. So this is going to be root 3 over 2 T1. So root 3 over 2 times T1 plus root 3 over 2 times T2 is equal to 100. And then this one, we can simplify this by multiplying both sides by 2. So we're left with root 3 times T1 plus root 3 times T2 is equal to 200. Okay, so we can even say T1 plus T2 is equal to 200 divided by root 3. I can leave it like that for now. That's like one equation. And then I can take the other equation, which is T1 sine 30. T1 sine 30, which is going to be a half T1. I can say minus, I'll subtract this from both sides, T2 sine 30, which is going to be a half T2, is equal to 5G, which is 50. So this equation leads us to this. Sine 30 is a half, so half T1. Subtract this from both sides. Sine 30 is a half, so it's a half minus a half T2 equals 5 times G, which is 50. So I can take this equation and I can make it simpler, multiply both sides by 2. So I can say T1 minus T2 is equal to 100. So I have equation 2. So I have these two equations, and I want to find the tension in the lower string. I need to find the tension in the lower string. Okay, so I can take these equations, these two equations, and I can subtract them. That will eliminate the T1. I want to be left with T2. So if I do equation 1 minus equation 2, T1 minus T1 is 0. T2 minus T2 is 2 times T2 is equal to 200 over root 3 minus 100. So T2 is going to be a half times 200 over root 3 minus 100. And that should give me my answer. So I've tried to keep things in exact form until the end, just to keep my answers more, precise. Okay, so I'm going to do a half times 200 over root 3 and minus 100, close the bracket, equals, and you get 7.7350. 7.7350 goes on. So we want to give our final answer to 3SF. So we can say, therefore, the tension in the lower string is 7.74 newtons. Okay, and there's the answer to this question. That's part A. Okay, that's part A of this question. Okay, that's the tension in the lower string. Okay, now we're going to move on to part B. All right. So part B says find the least value of x for which the block remains in equilibrium in the positions shown. Okay, so now, when you're talking about the least value of x for which it remains in equilibrium, we're thinking about what's called limiting equilibrium. Limiting equilibrium. Now, this is something which we normally associate with questions dealing with friction, where it's about to slip or about to slide. So how would we relate limiting equilibrium to this situation? And we want to find the least value of x. Now, if you think about it, so we have to think about the scenario where this will go out of equilibrium. So if you've got to think sometimes, use a bit of common sense and visualize the situation. Just imagine you were pulling on this mass and it's being held in equilibrium, fixed with these two strings to the wall, and it's being held in equilibrium. Right? If you reduce the force that you're pulling with and you keep reducing it, eventually what will happen is, if you think about the forces acting on this, you have the weight acting vertically downwards. Okay. Eventually what will happen is it will kind of start falling down. When it goes out of equilibrium, it will move down. At the point where it leaves equilibrium, it will go down. Okay? Because the force acting up will not be enough for it to keep it up. And what will happen is this string, when it starts going down, what happens to this string? This string will become slack, which means the tension in the lower string is going to be equal to 0. Okay, the tension in the lower string is going to be equal to 0. When it's in limiting equilibrium, the tension in the lower string will equal 0. So we want to find the point at which it is still in equilibrium, but the tension in the string is 0. So it's just on the point of leaving its equilibrium. That's what you have to find. Okay, so this string is just about to become slack, so the tension has just become 0 in the string, but it's still in equilibrium. So that's what we've got to take this case. If we take that case, then we can find the value of x for which this remains in equilibrium in the position shown. So again, we have to think about resolving these forces. So I'll just draw them again. I could use the ones from the other diagram, but we know that this is 30 degrees. Okay, so now I'm going to consider this as 0, so I can ignore this force. I can just think about the force of the upper string. Okay, so if you resolve that force this direction and in this direction, of course in this direction it's t times sine 30 going away from the angle, and here t times cosine 30 going into the angle. Okay, we ignored this force now, it's equal to 0. So if we resolve the forces horizontally, we have basically t cosine 30 is equal to x. And if we resolve the forces vertically, we have t sine 30 is equal to 5g. Okay, those are the forces that we can consider. This is now 0. Okay, so we want to find what x is. Okay, so we can eliminate t. We can do this in a few different ways. Okay, we can use substitution. I can make t the subject. Or I could even divide the two equations and I'll end up with tan 30 equals 5g over x. That's another way of doing it. I can do equation 2 minus equation 1. So I can do, I can do equation 2 divided by equation 1, which I'm going to get, the t's will cancel out. I'll be left with tan 30 is equal to 5g over x. Therefore, x is equal to 50 over tan of 30. And we can find the answer to that. So we are in degree mode, yes, 50 over the tangent of 30. And that gives you 50 root 3. 50 times root 3 newtons. If If we want to write it to 3SF, it doesn't say find the exact value. No, if it said find the exact value, leave it like that, but it doesn't. So we can round it to 3SF. That gives us 86.6 newtons to 3SF. 86.6 newtons to 3SF. And there's the answer for part B. Okay, we could have solved this in other ways. We could have, for example, made t the subject of both of them and said x over cosine 30 equals 5g over sine 30 and solved it. I think this is easier. We know that if you divide these two, the t's will cancel out, and we know sine 30 over cosine 30 is tan 30 from our identities that we learned in P1. Okay, so that's the end of this question. I hope that was clear. This is the second part of the question. You've got to think a little bit. It's a bit, you have to, it's something that if you haven't come across it before, you might not think about it. Okay, but now this has probably added to your, experience of these type of questions. But in this type of question, if you haven't seen something like this before, you have to kind of think and visualize the situation a little bit and try and think with a bit of common sense and imagine what would happen if you were actually pulling on this object, and if you were reducing the force, what would eventually happen? You will realize that eventually what will happen is that it will start dropping, and at the point that it starts dropping, this string will become slack, which means there will be no tension in the string. So we want to find at the point where it's at the limit, okay, of its equilibrium, where it's still in equilibrium, but it's just about to leave being in equilibrium, in which case this has become zero, but it's still in equilibrium. Okay, that's how we have to think. So that completes this question. It's a very important question here about statics. Other questions from this particular paper you'll find in the playlist that will appear at the end of the video. At the top here, you'll see a link for the playlist for this paper and a link for the playlist on statics of M1 for my Cambridge collection. I'll also put my statics playlist for my Edexcel selection here. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.